Assalamualaikum and good afternoon. So, this is our group for new material project. My name is ALIF NAUFAL.
My name is ILHAM.
My name is Toy.
My name is Lim.
We are from Group 2 and our group was assigned to design, fabricate and structurally test a solid circular bar made up entirely of uncooked spaghetti. Over the next few minutes, we will walk you through our engineering journey from the initial design concept to the final destructive bending test and the analytical calculation behind it. Let's begin with the background of this project. In mechanical and structural design, understanding how a beam behaves under bending loads is absolutely crucial. For this project, we use a common household item, which is uncooked spaghetti, as our structural material. While a single strand of spaghetti is highly brittle and snaps easily, bundling them tightly together allow them to share internal stresses. By molding these strands into a uniform circular cross-section, we create a composite structural member that can resist significant internal shear force and bending moments, mimicking real-world engineering materials like a concrete or steel bars. So, our project is driven by 4 primary objectives. First one is to successfully fabricate a solid circular bar that is exactly 30 cm long and 1.5 cm thick. Second one is to conduct a controlled destructive bending test using a hanging water bottle that is gradually increasing by hydrostatic loads. Third is to analytically construct the shear force and bending moment diagrams for every single loading intervals. And finally is to calculate the ultimate breaking stress and suggest a safe allowable normal stress using a specified factor of safety that is given is 1.5. Before looking at the test results, let's establish the geometric properties for our circular bar, which are vital for our stress calculations. The assigned thickness is 1.5 cm, giving us radius of 0.5 cm. Using the formula of solid circles, our cross-sectional area is calculated as pi r squared, which gives us 1.7671 to the power of times 10 to the power of negative 4 meters squared. Crucially, for bending analysis, the area moment of inertia is given by pi over 4 c to the power of 4. For our bar, this equals to 2.4850 times to the 10 of power negative 9 meters to the power of 4.
Okay, this is our spaghetti model, which has 1.5 cm of radius and 30 cm of length. And this is our first test for 250 ml of water. Okay, this is our first test for 250 ml, which is 280 grams. And let us start our test. Okay, so it didn't break, so it can withstand 250 grams.
So this is our second test. We're using 500 ml of water, which is 500 grams. So let's get started our test. Okay. As you can see, our spaghetti can withstand the 500 grams.
Okay, now is our third test, which is 750 grams of water. And now let us start. Okay, now as we can see, it can withstand 750 grams of water.
Okay, so this is our fourth test. We're using 1 liter, which is 1 kg for the weight. So let us try for this. Okay, as you can see, our spaghetti still can withstand for the 1 kg weight.
Okay, now is our fifth test, which is 1200 ml water, which is 1.25 kg. Okay, so let us start. Okay, so now we see it already break. So our spaghetti can withstand 1.21 kg of load.
understand the internal environment of the bar, we develop parametric question for a simply supported beam with a central point load. Because the load P is placed exactly at the center, the vertical reaction force at both ends are identical, equal to P over 2. For the first half of the beam, the internal shear force is positive P over 2 and the bending moment increase linearly as P over 2x. For the second half, the shear drop to negative P over 2. This means the maximum shear force anywhere in the beam is always P over 2 and the absolute maximum bending moment occurs exactly at the center point, equal to 0.075 P. Let's look at the detailed step-by-step calculation for our loading interval. For our initial load of 0.25 kg, the force is P1 equal to 0.25 kg multiplied by 9.81 meter square equal to 2.453 Newton. The internal shear force is V1 equal to 2.453 Newton over 2 equal to 1.227 Newton, and the internal bending moment at the mid-span is M1 equal to 0.075 multiplied by 2.53 Newton equal to 0.184 Newton meter. For the intermediate step, we follow the exact same method by simply replacing the value of P. For load 2, substitute P2 equal to 4.9050 Newton and it gives us a shear force V2 equal to 2.453 Newton and a moment M2 0.368 Newton meter. For load 3, substitute P3 equal to 7.3575 Newton and it gives us a shear force V3 equal to 3.679 Newton and a moment M3 equal to 0.552 Newton meter. For load 4, substitute P4 equal to 9.81 Newton give us a shear force V4 equal to 4.905 Newton and a moment M4 0.736 Newton meter. Finally, at our ultimate braking load of 1.2 kg, the force applied is P5 equal to 1.2 kg multiplied by 9.81 equal to 11.772 Newton. At this exact failure threshold, our internal shear force reach V5 equal to 5.886 Newton and the internal bending moment hit its absolute peak critical value and 5 equal to 0.8829 Newton meter. This final moment M5 at the center of the bar is what directly generated the internal normal stress that causes our spaghetti bar to break. Now let's determine the stresses. The maximum bending normal stress occur at the outermost top and bottom surface where y equal to c equal to 0.0075 meter. Substituting our peak bending moment at failure and our moment of inertia into the elastic flexion formula, sigma equal to mc over I. We find that our spaghetti material failed at an ultimate normal stresses of 2.665 MPa. To ensure structural safety in real world design, we apply the material safety factor formula, dividing our ultimate braking stress by our target factor of safety of 1.5. We conclude with a recommended safe allowable normal stress of 1.77 MPa. In conclusion, Group 2 successfully fulfilled all parameters of the SKTU2153 project guidelines. Our circular structural bar sustained a maximum load of 1.2 kg before experiencing sudden brittle failure. at the center line due to cross-sectional tension and compression. Our analytical model perfectly predicted the point of failure, validating that the peak internal bending moment of 0.8829 Newton meter govern the structure limit of our beam. With a safety factor of 1.5, the safe operating limit for this specific design is locked at an allowable stress of 1.77 MPa. Reflecting on this project, it has been an invaluable hands-on learning experience for our team. It allowed us to transition from pure textbook theory into physical engineering practice. Designing the mold and handling the spaghetti bundle taught us about real-world challenge like material imperfection and geometric consistency. Most importantly, it strengthened our communication and collaboration as a group. We would like to thank our lecturer, Dr. Amni Haslinda, for the guidance throughout this semester. Thank you very much for watching our presentation.